Hello people, as you might know already, my name is Richard and it has never changed. So today we are talking about chemical kinetics, which is the chapter 5 of the MCAT chemistry review. We are making progress. So when we talk about chemical kinetics, what we mean is the rate at which chemical reactions do occur. Most of us might be familiar with the term equilibrium, which tells us the balance point of a reaction, but not how fast the reaction occurs. Now, a reaction can be spontaneous, which means it happens on its own without outside interaction, or non-spontaneous, which also means that it requires outside forces to occur. Now, regardless of it being spontaneous or non-spontaneous, does not tells us how fast this reaction would occur. In fact, most biochemical reactions or biomolecular reactions would have taken lifetimes for it to complete if it wasn't for enzymes, which would increase the rate at which these reactions occur. Now, talking about the rate at which this reaction would occur will bring us into what we do called reaction mechanism. Now, reaction mechanism is the pathway with which a reaction would take. So reaction mechanism, let me write it here. A reaction mechanism over here is the pathway, right? Is the pathway a reaction would undergo to form products, right? Now, if I say a reaction mechanism is the pathway a reaction would undergo to form product, it brings us, it arises the question, so what pathway would a reaction undergoes to form products? Let's consider this reaction, this generic reaction over here. A2 plus 2B forming A2B. Now, all we do know about this reaction over here is that 1 mole of a compound A combined with 2 moles of compound B to form A2B. Barely or rarely does this balance equation of the reaction, is it balanced? It's not truly balanced. But rarely is this that will this equation, right, determines the actual pathway or tells us the actual pathway of the reaction. Now, this reaction could have undergone two separate pathways, like pathway 1 and then pathway 2, combining 1 and 2 to form this reaction. So pathway 1 could have been that this reaction first underwent A2 plus B to form A2B, 1 over here, and this could be either fast or slow depending on this could be either fast let me say this one is the slow one, right? Let me see, this is the slow one, right? And it could, this is 1, and the second pathway is combining this, right? The product that it has formed over here, A2B plus another B to form 2A2B, right over here. Now, this reaction, so if we are supposed to balance here, I'll bring 2 here, and then this equation would, if I bring 2 here, I should bring another 2 here to make this equation balance, right? So now that we have this equation balance, and this would have been the fast pathway, right? So the equation A2 plus 2B to form 2AB, if we balance it, if it's actually balanced, we know that 2 moles of compound A combined with 2 moles of another compound B to form this reaction, right? Now, this reaction could have undergone 2 separate ways. One is 1 mole of A combining with 1 mole of B to form A2B. And this product here that is formed, right? This product here that is formed would combine with the B again to form 2AB, and it will be a fast reaction. Now this reaction might not be determined at all, or it could not be the first one is very hard to measure or determine at all, because sometimes the rate at which this compound is forming, which is A2B, it is also being consumed at the same exact rate, so which makes it like cancels out, not resistance in the equation, right? So it is hard to determine this compound. So since it is very hard to determine the rate at which this compound is forming, and is also being used because you cannot time one and leave the other, would limit us to using the slow phase of the reaction to determine its rate. Now the slow phase of the reaction, which is this one, right, to determine the rate. So when we talk about the rate determining stage of a reaction, the rate determining did I got it right? Determining stage is the slowest stage of a reaction, right? The reason why this is so is because you are only as strong as your weakest link. If we are going to determine the rate at which a reaction is occurring, we have to use the slowest stage, because that is what it is factually measurable, that we could measure how these compounds are being consumed, or how much of these products are being formed. Now, once that we have this thing in common, there are different types of reaction mechanism, right? So meaning there have been different theories proposed to understand how the molecules of these compounds would combine to form these products. The first theory over here that we do know is the theories are called the molecular basis of chemical reaction. The molecular basis of chemical reaction, right? And when we talk about the molecular basis of chemical reaction, it is basically telling us how the molecules of these compounds would combine to form the balanced equation, or combine to form the products. Now the first one that we do know is the collision theory of chemical kinetics. So the first one over here, one is the collision theory of chemical kinetics. This theory states is that the rate, right, of a reaction is proportional to the frequency with which the molecules collides with each other, right? Collides with each other. Now, this is the collision theory of chemical kinetics. The rate of it states that the rate of a reaction is proportional to the frequency with which the molecules collides with each other. So the rate of a reaction, let's say R, is proportional to the frequency, let's say Z, right? The frequency with which the molecules collides with each other. And then the frequency with which the molecules collides with each other is measured in per second, right, over here. But the rate goes on to express that not all collisions are or not all collisions will result in a chemical reaction, right? Let's say we do have, for instance, if we are still using this, right? If we have like A2, we have, let's say, compound A2 over here, like element or whatever, A2 over here, combining with like 2B over here, or B over here, right? Now if these is supposed to crash into each other, right? So they, let's say they crash into each other over here, right? If they crash into each other, if they are going to result in bonding towards each other, if they are going to result into becoming one bond, as in over here, they're going to result into becoming this bond, which basically depends on, right? What basically depends on if the energy that existed between, or if the rates which they crash, or the energy that they release in the crash is enough to break their original bonds to form this new bond. So not all, in other effects, not all collisions are effective. This is what I'm trying to mean here. So if not all collisions are effective, this sign of proportionality would change to being that now the rate of the reaction, right, will be equal to Z, which is still being the rate at which the molecules are combining with each other, times F. Now where, let me see, Z is equals to the rate with which the molecules are colliding with each other. And then F now becomes collisions that results in a successful chemical reaction. Right? So now this becomes the new equation of the reaction. Now for a collision to overcome its chemical reaction, the energy with which it hits each other or collide, these molecules collide with each other, would have to overcome the barrier, the energy barrier in the reaction, which in some terms is called the activation energy. If they collide with enough energy to overcome the activation energy, then, or to overcome the energy barrier, then they're gonna fuse together to form one compound over here, as in as we know as 2AB. So now that becomes the collision theory of chemical kinetics. Now moving towards a more complex approach, which I am not going to, the chemical theory of the collision theory of chemical reaction could also be explained using the Arrhenius equation. So the Arrhenius equation, right? The Arrhenius equation states that K, which is rate constant, is equals to AE, and all this A, right, is to the power of negative E over RT. Now you can memorize this equation or not, that is up to you. But what the MCAT would really test on this equation is not how to plug in and check, because it involves natural numbers like the Euler's number and then the natural logarithms, which is in, and those calculations are complex to make. It will test you on the relationship that exists between the variables of this reaction. Over here, we have, if we are supposed to define this term, as I said, the K over here is equals to the rate constant, as I said earlier, the rate constant, right? And then the AE over here would give you the frequency factor. The frequency factor. So the frequency factor is basically how much molecules, or how the molecules are colliding with each other. And this and this RT, whatever, R is the gas constant and T is the temperature. So T is the temperature, right? Now from here we can draw an inference that if AE increases, the rate constant is going to increase, which in turn going to increase the rate of the reaction. But one thing that you need to pay attention over here is the relationship that exists between K and temperature. Now, under normal circumstances, using common sense, you know that if we increase the temperature in a system, we will eventually end up increasing the rate of reaction because the molecules are gaining more kinetic energy as we increase its temperature. But over here, right, in this equation, if we increase the temperature, right, we are going to have a much more smaller value over here, and we having a much more smaller value over here would in turn mean that we are going to have a smaller AE, and a smaller AE is corresponding to K. So which means that we increasing the temperature, this is in arithmetical sense, means we increasing the temperature is going to reduce the frequency factor, and in turn reduce the rate of the reaction. But no, you should know that it has a negative sign over here, and negatives are really important in when you are dealing with physics and chemistry on the MCAT, because they will tend to trick you. If we increases the temperature over here, not reduce, if we increases the temperature over here, what we eventually end up doing is that we move this value. See, this value is always going to be negative. This whole thing is always going to be negative because there is a negative sign over here. So if we reduce it, we are going to have a smaller negative number. So a smaller negative number means we are approaching towards a more positive number. So let's say we have a number line. This is 0. Over here is the positive side, and over here is the negative side, right? And this number was going to give us a negative, let's say a -2 over here anyways, right? If we reduce, if we increase T, it means we are reducing the entirety of this figure up here. So if we are reducing the entirety of that figure up there, it means we are going to reduce the negative value. So let's say we reduce it to something like -1, right? Now we have moved from a more negative way, which was 2 over here, to a more positive value. Like we're going towards more positive, and that means we are becoming bigger and bigger, if you do understand what that means. So that is how you should, that is the relationship that would exist between the temperature and then the rate constant of the reaction. Now the next molecular basis of chemical reaction is what we call the transition state theory. Transition state theory. So 2 is the transition state theory. Now when we talk about the transition state theory, it states that in a chemical reaction, right, there would be, the chemicals would combine or will collide with each other to form a transitional state product. And this transitional state product will either be consumed at a rate that at which is being formed, just as over here, to go ahead and produce what we call the product. And this, in other words, is called, it will form what we call the activated complex, right? Now don't mind these pink slips. So if we have, let's say, a compound, same, right? Right, there is a bond between AA and then BB. Over here, there is a bond between A and then B. If these compounds are combining to form, let's say, our product over here, which is A bonded to B and then another A bonded to B. So this, in the first way, we had a compound A bonded to A and then B over here, right? B is existing, it's just a gas because it's just one see over here A2, meaning there is two of these A atoms combining, existing as a molecule, and over here is just two moles of B, meaning it's just one B atoms. Now if you want to break this bond that exists between A, B, right, A and A, to make this A bond to this B and this A bonds to this B, like as it is over here, they are first going to form a transitional statary bond, which is, say, A over here, and then B over here, B over here. Now there is going to be part of this bond will be broken, and then partial of these bonds are going to be formed. So we could put this in a bracket over here, right? So this state is what we call activated complex. This is what we call the activated complex, and it is represented by this cross sign over here to form the product that we finally need. Now, so realistically, if we are supposed to plot a graph of the Gibbs free energy, right, where we have over here the Gibbs free energy, right, and then we have over here the reaction coordinate. The reaction coordinate of the transition state theory, we know that for any reaction to occur, right, these compound, which is AB, AA, and then BB, already have some type of energy that is existing between them. So let's say their energy starts from here. Now, for them to occur, they have to collide with enough energy to reach what we call the activation energy over here, right? So the activation energy, EA, over here. And when they reach over here, let's say that A plus B, let's use real compounds for instance, like a hydrogen gas and then a chlorine gas over here, right? Now this is them when they are reactants. They have some type of energy which is over here. They collide with each other, gaining enough energy to reach to the activation energy. Now once they reach the activation energy, they form the activated complex, or which is the transition state, right? So the transition state of these compound would exist somewhere between here, whereby the bond, so if we are supposed to draw the bonds that existed between them, the old bonds will weaken and the new bonds would begin to form. So let's say HH over here, and then Cl, this is bonded to this, and this is bonded Cl over here. This HH bond will begin to weaken, right? And then the HCl bond will start to form. Now that this complex has formed, this complex have more energy than the product, the reactant that it started with. So what goes on from here is that this complex will now dissociate, right, to form the activated complex of the reaction. To form the activated, it will dissociate to form the product. So when it dissociates, it will come somewhere down here, right? So when it dissociates and reaches this level, when it dissociates and then it reaches this level over here, the energy that it's used from this bottom up here all the way to the top over here, right, becomes the activation energy, and then the product that is formed up here is the activated complex. Now once it comes over here, the bonds, it now has the same energy as when it started with, right? And the bonds are continually weakening and forming. So once it gets here, the reaction doesn't stop here. It will go until all the reactants are turned into products, where we're going to have HCl as a product over here, for the balance equation, 2HCl as a product over here. Now the energy that exists between over here all the way down to the lowest energy that the products hold is what we call the change in the Gibbs free energy, right? The change in Gibbs free energy, and it's going to be negative, because when we started we had a higher energy that started up here, and then we reduce our energy down here, right? So all over here, the energy that existed between this, the Gibbs free energy, is going to be minimal. Now the overall entire, if you want to reverse the whole reaction, right? If you want to reverse this whole reaction, right, we have to gain the energy that we lost, the Gibbs free energy that we lost. So we have to gain it. A heat has to be added into the system for this to reach up to this point. That is why when HCl is aqueous, we have to add heat to boil it to get to the H2 gas and then the chlorine gas over here, right? And continuous boiling them for it to reach up here, so that we could like reverse the reaction, right? So those are the various energies that are involved in the Gibbs free energy versus reaction coordinates graph. Now from here we are going to move on to factors that will affect the rate of a reaction. So we are moving to factors affecting the rate of reaction. Factors affecting reaction rate, right? So the first factor that we are going to talk about here is temperature. Let's first talk about concentration. So one is reaction concentration. Concentration. Now let's think about this logically and bring equilibrium into this reaction too, in the lines of equilibrium. Let's say for example, we are still using our generic reaction over here, A2 plus 2B. Let's say we are still using our generic reaction over here, A2 plus 2B, going to form 2AB over here, right? If we increase the concentration of the reactants over here, so let's say these two exist in a jar, right? A is over here, A is these black dots that exist in the jar, and then B is these orange dots that exist in the jar. If we are supposed to increase the overall concentration of both reactants, now we are going to have more stuff, like more B in it. We are also going to have more A in this thing. So by so doing, we are increasing the chances of these things colliding with each other. And if we are increasing the chance of these things colliding with each other as we come over here, the rate of the reaction is directly proportional to the rate with which the molecules are colliding. So we are increasing the rate with which the molecules are colliding, which in turn will inherently increase the effective collisions also. So thereby, if we increase the concentration of the reactants, we increase the rate of the reaction. Of course, more and more of these stuff are bombarding towards each other, and we are forming more products. So rate concentration increases the rate of reaction. Now that is said, the second one that I also want to talk about over here is the temperature, that we actually talked about it over here. Now the second one that I want to talk about is the temperature. So basically it follows the same thing. If A and B is also in a gas form and then I increase the temperature, which I would in turn increase the overall kinetic energy of them, they are going to now have more kinetic energy to move around more and hence bombard with each other a lot more. And by so doing, I increases the rate at which they hit with each other, Z, and then the effective collision. So thereby increasing the rate of the reaction. So temperature would also increase the rate of reaction. So temp will increase the rate of reaction. Next factor that would also increases the rate of reaction is the medium, the reaction medium. So for the medium, what we are stating is that the medium with which the reaction occurs in, whether it's being acidic environment, aqueous environment, or alkaline environment, would have some form of effect on the rate with which a reaction would occur. And some compounds would prefer to react in aqueous, acidic, or alkaline environment. For instance, some enzymes act best in acidic environment, some act best in alkaline environment. So a medium would also affect the rate with which a reaction would occur. Now, as would the reaction increase, the rate increase or decrease will now determine on context as to which the reaction is. So let's say, for instance, in your stomach where we have salivary amylase, when they move from your mouth to your stomach, which your mouth is more we say alkaline than your stomach, they are denatured and hence they cannot perform better in your stomach. So it works that way. The medium will determine on the context. As for concentration and temperature, whether you are reducing it or increasing it is going to have a direct effect on the rate of reaction. And also a catalyst. Catalysts are basically, sometimes they are enzymes or sometimes they are other substances that are added to a reaction to increase the rate of the reaction. Now, what do catalysts usually do? Sometimes they increase the overall surface area for the reaction to occur. Sometimes they come with other energy. They come with energy that they would literally bond to the reactants and give them this energy to move faster, to collide with each other. Now, if you add a catalyst to any chemical reaction, you are supposed to get back the catalyst intact at the end of the reaction. Catalysts do not become or do not form they don't become a product of part of the reaction. A catalyst could be heat it could be an enzyme, right? They are all different forms of catalyst. So if I'm supposed to go a little bit intricate, what catalysts do is that they reduce the activation energy of a reaction. So if I have a reaction that occurs like this, right, and I rose over here, as I said earlier, the up to here is activation energy, right? That is E. Now and this is the uncatalyzed pathway, right? Now if I decided to take a catalyzed pathway, what the catalyst will do is that it will reduce my rate, right? But it will reduce my activation energy, the energy I needed to overcome here. So this is the catalyzed pathway. Now, as you might know, it just reduced the activation energy for the reaction to occur. It did not have any other effect on the rate of reaction than decreasing the activation energy. So that these factors affects the rate of reaction: concentration, temperature, medium, and then catalyst. Alright guys, thank you for watching this video. We would end here, and then next time we will continue and dive in depth into determining rates and how we determine rate laws and calculation of rates. So let's end here and continue tomorrow. Thank you.